An alternate approach to modeling a two-terminal linear circuit as a voltage source in series with a resistance is to realize the circuit as a current source in parallel with the resistance, which is Norton's theorem. Norton's theorem and Thevenin's theorem are very similar. They just interchange the roles of voltage and current. To put Norton's theorem in context, I'll briefly review the underlying concepts relative to Thevenin's theorem. The goal in Thevenin's theorem was to determine a simplified voltage-current relationship at two terminals of a potentially complicated circuit. To obtain a model of circuit A, we look at the terminals of interest to us. We want to determine a mathematical relationship between the voltage and the current at these terminals. To create this model, we applied a hypothetical current source at these terminals and calculated the resulting voltage. The resulting model consisted of a voltage source in series with a resistance. As with Thevenin's theorem, Norton's theorem models a circuit as a voltage-current relationship for a two-terminal network. The terminals we select are still those that interconnect the circuit with its load. However, the approach to finding the voltage-current relationship at these terminals is slightly different for Norton's theorem. In Norton's theorem, we'll apply a hypothetical voltage source across the terminals and calculate the resulting current. As with Thevenin's theorem, Norton's theorem will use superposition, which again means that the circuit we're modeling needs to be linear. Recall that in superposition we examine the effect of each source individually and then sum up the contributions from all the sources. We're now using a voltage source to find our voltage-current relationship. So our first step will be to determine the current due to that voltage source, which I'll call I1. To do this, we kill all of the sources inside circuit A, which leaves a purely resistive network. This is identical to the first step in Thevenin's theorem. The equivalent resistance of this network is still the Thevenin's resistance and is still represented as RTH. The difference between Norton's and Thevenin's theorem is that the voltage is our independent variable, and we want to calculate the resulting current. We still use Ohm's law, but the roles of V and I are reversed. Ohm's law says that the current I1 is equal to the voltage V divided by the Thevenin resistance. Next, we determine the current due to the sources inside the circuit, with the voltage source outside the circuit killed. Killing a voltage source converts it to a short circuit, so the voltage difference across these terminals is now 0. I'll call this contribution to the terminal current I2. Keep in mind that during this step, all of the sources inside circuit A have been restored. Since the terminals are short-circuited, the current from this step is called the short circuit current, which is commonly called I sub SC. It's typical to define ISC in this direction, which is the opposite direction to our sign convention. Thus, I2 is the negative of ISC. Now we superimpose the contributions from the previous two steps. The resulting expression for the current as a function of voltage across the terminals is this. The current due to the external voltage source is V over RTH, and the contribution due to the sources inside the circuit is the negative of ISC. This equation can be represented by a circuit as shown here. The current through this resistor is V over RTH, so I is equal to V over RTH minus ISC, which agrees with the desired equation. This circuit is the realization of this equation. Ultimately, Norton's theorem says that any linear circuit can be modeled as a current source in parallel with a resistance. Mathematically, the voltage-current relationships across the terminals of these two circuits are identical as long as RTH and ISC are chosen correctly. The resistance, RTH, is the resistance seen across these terminals with the sources in circuit A killed. The current is the current that would be through a short circuit connecting these two terminals. Now let's do an example of Norton's theorem. We're going to use Norton's theorem to replace everything except for this load resistance R with its Norton equivalent, and then we're going to find the resistor current, I, if R is equal to 4 ohms. So this is our circuit A. if these are terminals A and B, we want to find a current source in parallel with a Thevenin resistance that gives me the same voltage-current relationship at these terminals. I'll find the equivalent resistance first, and then we'll find the short circuit current. To find the equivalent resistance seen across these terminals, or RTH, the Thevenin resistance, we kill the sources in this circuit. The current source becomes an open circuit, the voltage source becomes a short circuit. Then we find a voltage-current relationship across these terminals. I can do that using circuit reduction techniques. These two resistors are in parallel, so its equivalent resistance is the product of the two. 3 ohms times 6 ohms over 3 ohms plus 6 ohms, which turns out to be 2 ohms. This resistance is then in series with this 2 ohm resistance, so RTH, which is the ratio of this voltage to this current, is 2 plus 2 or 4 ohms. Now let's connect a short across the terminals and find the short circuit current, ISC. To find the short circuit current, ISC, we connect a short across terminals AB, replace the sources in this circuit, and calculate this current. This looks like a good application for nodal analysis. I'll make this my reference node, 0 volts, and I'll make this VA. This is a dependent node, so it's VA minus 6 volts. Now if I do KCL at the super node A, I get minus 2 amps for this current source plus this current, which is VA minus 6 volts over 6 ohms, plus this current, which is VA minus 0 volts over 3 ohms, plus this current, which is also VA minus 0 over 2 ohms. That sums to 0. If I multiply this through by 6, I get negative 12 plus VA minus 6 volts plus 2 VA plus 3 VA is equal to 0. So 6 VA is equal to 18, or VA is equal to 3 volts. To find the short circuit current, this is now VA, which is 3 volts minus 0 over 2 amps. So ISC is equal to 3 volts over 2 ohms, which is 1.5 amps. Now let's use the Norton equivalent circuit we found to find the resistor current when the resistance is 4 ohms. Our Norton equivalent circuit is a current source whose current is ISC, or 1.5 amps, in parallel with a Thevenin resistance, which is 4 ohms. Then I reconnect my resistance R across these terminals. These are still my terminals AB. This is my load resistance R, which I say is 4 ohms. And I want to find this current. This looks like a current divider now. So I is equal to the total current, 1.5 amps, times the other resistance, 4 ohms, over the sum of the two resistances. So I is 1/2 of 1.5 amps, so I is 0.75 amps. Thevenin's and Norton's theorems say that a voltage source in series with a resistance can be alternately represented by a current source in parallel with the same resistance, and vice versa. That means that either of these configurations can be converted to the other using a process called source transformation.